All right, Algebra 2 people, this is our last section before we test. I believe we're going to test over, I believe it was 6, 5, 6, 6, and then 7, 1, 7, 2, and 7, 3. And we'll be testing here real soon. Today we're going to talk about E, and we're going to use functions involving E. And to give you a little heads up of where this comes from, in the past, let me get a piece of paper here. In the past, we learned about this formula. It was the exponential growth model, where it was like you got some starting amount, and then you've got this 1, and that kind of represents your starting amount in a way. And then you add to it a rate, and then raise it to some time. And you could use that to calculate the exponential growth of things. And then the same day we were introduced to an adaptation of that formula that was like this. Basically, it's got all the same characters in it, but you divide your rate by n, and then you multiply your time by n. And I may have described this as being more accurate. What this does is it's the compounding interest formula, and what it does is it splits your rate up over the year, but it calculates it more often, and it approaches more closely what things in nature do. Well, today we're going to take it a step further. Today what we're going to do is we're going to think about things that grow continuously. They don't wait at all to grow. They grow all the time. And when you do that, what you would do is, if you're going to be growing all the time and adding that growth back in, you're going to increase the number of times that it's compounded to infinity. You're going to raise this to infinity and this to infinity. And what happens is, when you do that, you get, oddly enough, this formula. And a lot of people will think of it as PERT. Notice it's still got the rate, it's still got a time, it's still got the initial amount. But you use this formula when things grow continuously. Things in nature grow continuously. Also, I think you can do academic, or not academic, but, money formulas with continuously compounding interest. I think there's people that do that, and I'm not positive on that. But it's definitely used for things in nature that grow. Now, because of this formula and because of its widespread use in this world that we live in, it's got this E in it. It's not another variable. It's a number. And today, we're going to work with E. And I've got a couple of sentences here to kind of frame this for you. You can add E to the list of special numbers. Now, some special weird numbers that we've learned would be like I. If you recall, I represents square root of -1. It also stands for imaginary. And also another special number that you learned and you spent a lot of time with in geometry was pi. Pi is the measure of circumference of a circle divided by diameter, but in truth, you can never really have a perfect circle. And so you can keep refining that calculation indefinitely. And that's why pi is irrational. It goes on forever. Turns out E is more like pi. Okay, I is very, very unique and special, but it's used in imaginary numbers. But pi is irrational, and so is E. E is irrational, and it's the number found by increasing n to infinity. Now I mentioned that in my little intro. It's the number found by increasing n to infinity, but it's actually for just a component of that compound interest formula. So if you take 1 plus 1 over n to the n power, now notice that's found in the compound interest formula, but if you raise n to infinity, you approach the value of e. Now it's interesting because there's kind of this competition. There's if you make this number bigger and bigger, it's going to overall be approaching 0. It's never going to get there though, but it's going to get very, very small. If you have out here numbers getting bigger and bigger, that's going to make the overall numbers, the overall result, bigger and bigger. So you got this getting smaller, this getting bigger. It's interesting that when you start calculating this, E is approximately 2.71828. But because you can never get to infinity, you can keep refining this number and getting it more and more accurate forever. So when people ask me what the value of E is, I say it's about 2.72. You know, that's a decent estimation of it. And again, just so you have it in your notes, E's vitally important because of, whoops, put that as an exponent, because of PERT, the continuously compounding interest formula. Hopefully in your math careers or in your job careers, your career careers, you get to use this formula a little bit. Okay, a little bit more information. Just like pi, you can leave answers in terms of E. So if you recall in geometry, sometimes they would ask for the exact answer, and so you might get an answer like 6 pi centimeters. Well, the reason they're doing that is because you might have to do more calculations later, and you don't want to introduce like a rounding error. But that's an exact answer, okay? And we're going to do that on some problems. We're just going to leave E as it is. But other times, or you may be asked to approximate an answer with a calculator. Now, there's a button on the calculator. Let me see if this shows up here. I think it will. Okay, I'm using this graphing calculator here, but it looks similar to a lot of you. The E is found in conjunction with the natural log. It's called ln, and we haven't talked about logs yet, but we will later. But ln, it's usually the second option, and there's e to the x. Now you might be thinking, well, why is it e to the x? You know, we have a pi button, which is just pi. Why is it e to the x? Well, it's because of the way it's used. E is really only ever used in conjunction with an exponent, with that formula right there. So they just make it automatic. Now, if you forget what the value of E is and you want to know, just on my calculator, I'll do second E, and then I'll just raise it to the first power. And there you have it. There's the rounded answer for what E is equal to, 2.718281828. All right, so that's how you do it. Please, I encourage you, grab whatever calculator you have. Some of your calculators, you're going to have to press 1 first, then do second, and then e to the x to evaluate that. But please grab a calculator. Make sure that you can put 1 in and get the value of E. All right, so here's what you're going to be expected to do. you're going to be expected to do some problems that just say simplify. And on these problems, you're going to do basically properties of exponents, to be truthful with you. And then other problems, it's going to ask you to use a calculator and punch in the numbers in and round your answers. So let's start out with some simplified problems. E to the 9th times e to the 6th. Well, we're just going to simplify it, and to do that, we'll use properties of exponents. Same base, you're multiplying. What do you do with the exponents? You add them, and you get e to the 15th, just like that. And because it says simplify, we're going to leave our answers in terms of e. We'll just leave it e to the 15th. Let's try another one, just a little bit of practice here. 60e to the 8th, but we're dividing by 12e to the 3rd. Well, let's go ahead and simplify this fraction. 60 divided by 12 is 5. And now, class, when you're dividing, you subtract the exponents, and your result always goes on top. So we're going to do 8 minus 3, which is e to the 5th, and we just put it on top. We put it in the numerator. There's no denominator. Well, I mean, it's 1 in this case, but the e to the 3 just goes on top with the 5. And we're done. Let's try another one just for added practice here. Parentheses, negative 10, e to the negative 5x. Now this is going to be kind of strange because you haven't done properties of exponents too often when you had variable exponents. And so this is kind of a new thing, but you're still going to use the same properties of exponents. So there's actually a couple ways to do this one. One way to do it is to recognize, oh, negative exponent is going to move down. It's going to make it the reciprocal. It's going to move below the negative 10. You could do it that way. Another way to do it is the way I'm kind of preferring to do it, is to notice this 3 on the outside, and notice you've got a product. And the product property, well, actually, this is the exponent. Power of a property, or power of a product property. It's kind of a mouthful there for me. But what happens is the 3, people think of it as distributing, but it's really not. The 3 is going to be the exponent for both of these bases that are multiplying. So we're going to get negative 10. Now I'm going to put it in parentheses because the negative also needs to be raised to the 3rd. And then we're going to get e, and then when that power meets that power, they multiply. Power of a power property, you multiply them, you get negative 15x. Now from there, I've got 2 more things to do. I need to actually punch that in my calculator. We do want to evaluate that part. We'll leave e alone. But we'll get negative 1,000. And then e to the negative 15x, because it has a negative exponent, it'll become its reciprocal, and it moves to the bottom. And we're done. Now, how you know you're done is when you only have one base. So here you got 2 of them. You simplify it down 1 base. And there's no negative exponents to move. And also, you've simplified any just plain old numbers that are raised to a power. All right. Now, I promised you that also you'll be expected to do some problems where they say use a calculator to evaluate. And so let's just try one of these out. E to the 6th. Well, you'll grab your calculator. You'll do, on my calculator, I'll do second and then get the e to the x button. And then I'll put a 6 in, and I get 403.43. We'll round it to the nearest hundredth. If you're not getting that, try it a different way. If you're still not getting it, please talk to me tomorrow in class. Let's try out e to the negative 0.28. e to the negative 0.28. You could do properties of exponents, move this down, and then punch it into your calculator and have it 1 over. But that's actually not a good way to do this because we're going to have an irrational number. We're going to want to round our answer. So I suggest you just go ahead and grab your calculator, enter it in. 0.76. Again, if you're not getting that, try it a little bit different way. I may need to see how you're doing it, so you can talk to me tomorrow if you're having trouble with this. And then finally, 1/2 e to the exponent 0.4 times 2. Now you can almost see the resemblance of this with the PERT formula, the continuously compounding interest formula. So for example, this might be like a puppy that weighs like or kitten that weighs like 1/2 pound, but it grows 40% every, we'll say month, and then you want to know how much it weighs after 2 months. This is the setup for it. But to evaluate this, let me give you some pointers. Common mistakes are people do e to the 0.04 and then do times 2, and it ends up calculating the e to the 0.4. It calculates that and then times your answer by 2. So to avoid that, you could actually add some extra parentheses in there, or just evaluate this mentally first. So in my calculator, I'm just going to do 1/2, which I'll just do 0.5, and then e, and then it's going to be 0.8. And rounding to the nearest hundredth, I get 1.11. And there you go. Okay, flip it over. We can also graph functions with e. So our instructions are to graph, and along with it, we're going to state domain and range. And we're going to start out with y equals 4e to the 0.5x. Looks kind of wacky. But you're going to do this the same way we do other exponential functions. We're going to think about if there's going to be a shift in the graph. If there is a shift, we're going to do the non-shifted version first, then shift our coordinates. But in this case, because we're not adding anything with the x, we're not adding or subtracting anything down here on the ground afterwards, there's going to be no shift here, and that's a good thing to know. From there, make a table of values, and we'll just use the same values that we normally do with exponential functions, -2, -1, 0, 1, and 2. And you're going to enter each of these into your calculator. Now I'm just going to run through it really quick, but if you need to pause it in order to catch up, that'd be fine. But you're going to get 1.47. 2.43, 4, 6.59, 10.87. Sorry, I did that one quickly because the 0 makes it e to the 0 power, which is 1, and then 1 times 4 is 4. But anyway, yeah. Graph each one of those. And now, class, what's a little bit tricky about this one is because they're all above 1, it's tempting to think that our asymptote is going to have an asymptote. It's going to be at y equals 1. But the thing about that is that the only way that our asymptote would be at y equals 1 is if we had a shift. And since there's no shift, you can confirm this by using more points, -3, -4, -5, whatever. You would find out that this, in fact, has an asymptote at 0, not 1. It'll go on down. All right, so there's the graph. Our domain, no restrictions, all real numbers. You can use whatever you want. Our range, though, the smallest y value is 0, but we never get there, and our biggest y value is infinity. Okay, let's try one more, and we'll call it quits for the day. Same instructions, we're going to graph. This one's significantly more complicated. We've got e to the negative 1.5, x plus 2, and then back down on the ground, we got -4. Does this have a shift? You bet it does. It's got a shift. What you add with the x part is going to be a horizontal shift. It's going to be the opposite of what you think, so it's going to be left 2, and the -4 just moves it down 4. Now, because there's a shift, I'm going to start out by doing the non-shifted version first. And you keep the negative 1.5, you keep the x, you just get rid of the shifting part. And you'll punch all those in. You'll graph each one of those. That one's way off. We'll just mark it out. We won't worry about that. Now, before I connect them, I want to think about the shift. And before I shift my points, I'm going to think about the asymptote. The asymptote starts out at y equals 0, but when it moves down 4, my new asymptote is going to be at y equals -4. That's my asymptote. And that helps me when I graph not to blow past the asymptote. So we go left 2, down 1, 2, 3, 4. Left 2, down 1, 2, 3, 4. Since I'm using a different color, I'll make dots, but a lot of times I'll make X's just to keep them different. Left 2, down 1, 2, 3, 4. Left 2, down 1. Okay. And then connect those dots. Don't cross your asymptote. And there we have it. Now for our domain, all real numbers, but our range is going to be y is greater than -4. But in interval notation, we're going to say -4 to infinity. Okay, the last thing that I'd like to talk about is kind of a big deal. E is approximately 2.72. We've learned that when the base of your exponential function is bigger than 1, it's exponential growth. And it was. We're going away from the asymptote as we go left to right. But a curious thing happened on our second graph. It's actually exponential decay. It's going towards the asymptote as you go from left to right. Well, aside from having an E in it, this problem also had something that we haven't seen before with exponential functions. And that is a minus sign in the exponent. What that actually does, class, is a negative makes the base its reciprocal. So 2.72 is bigger than 1, but 1 over 2.72 is less than 1. And when your base is less than 1, it is an exponential decay function. So let's write that down at the bottom here. The negative exponent creates a decay function. So if you have E, you will look at the exponent to determine if it's growth or decay. Growth, because it's, growth because it's positive. Decay, because it's negative. Simple as that. You're going to want to practice these, like, seriously. You're going to want to practice them. Page 495, numbers 1 through 18 all, 19 through 49 odd, and I'll make sure to get you some graph paper as well. Thanks so much for watching. Have a great day.